Welcome to another basic machine learning tutorial. In this project, we'll use linear regression to predict the resale prices for housing properties. In just a few moments, we'll jump into hands-on coding where we'll implement linear regression to predict the resale flat prices using HDB dataset. We'll cover basics such as importing and analyzing data, understanding insights from EDA, building and evaluating models. Along the way, we'll learn how to pre-process data using various methods including label encoding and one-hot encoding. We'll also get a practical understanding of how linear regression works. Feel free to use the chapter markers to skip around. That said, let's get started. The data we are using today was downloaded from data.gov.sg website. You'll find the link in the description below. Download the CSV and save it in a local folder named Data. For setup, I'll continue using Google Colab for this project due to its short setup time. We'll mount Google Drive first since we need the data folder path when we start the project. Check out my last tutorial for detailed instructions on how to get started with Google Colab. Okay, let's title the project Predicting HDB Resale Price. Good. We'll start with imports as usual. First, import the required libraries that we know we are going to use. Then declare constants, the variables with fixed values that we'll reuse throughout the project. For now, we only have our data path. Perfect. We're ready to load and overview data. We'll use pandas read CSV method to load dataset. Okay, time to check out the dataset. Lovely. Now that we have the data loaded, let's explore it a bit. Take a look at the shape. So our data set has over 180,000 rows, which is a lot of information to work with. There are 11 columns, meaning we have 10 features, and then we have our target column. Let's take a deeper look using head for the first 5 rows. And tail will give you the last 5 rows of the data. Great. What shall we do next? We'll take a look at the features and look for missing data. We have the features related to sale of apartment here, and we have resale price, which is our target, and that is in float data type. Awesome. All of our columns are non-null. You can also see the number of rows here. No missing data, and that's always a relief. Many of the columns are in object form, which means they contain string or text data, and with only a few of them in numeric formats. All right, next is feature overview. Feel free to pause the video here and inspect the data yourself or follow along as we analyze the various features. Let's dive right in. First, let's make a backup of our data so we can always fall back on it just in case. Then we'll go through the columns using df.columns and check them one at a time. All right, start with the first column. What was it? Okay, here we go. df.month.head. Right. Month column is in year month format. We'll probably just use year for now. We might consider using month to see if that affects prices. Are there seasonal variations and so on? For now, we'll need to split this into 2 columns, one for year and one for month. We can separate the values by splitting the string like this. First 4 characters for year value, and everything that's after the first 5 characters because of the colon will be the month value. Okay. We can even plot their value counts into bar charts to get a better look at the distribution. Here's the distribution of the year values in our dataset. Let's do the same for month values. Great. Next is town. So let's do a df.town.head. These are all string values. Let's try df.town.unique. We can get the unique values this way. There are quite a few unique towns. Let's see how many. Length 26 in total. We'll keep this column, but we will have to convert this to numeric by encoding it later on. Let's check out the distribution using similar code as we did before. We can see that some towns like Sengkang and Punggol have way more entries than towns like Bukit Timah. Okay, there is some imbalance. We'll talk about this in a short while. Next is flat type. How many flat types do we have? Okay, there are 7. It's also a string, so we'll have to apply encoding here as well. Let's check the distribution. Again, we can see that some types like 4-room, 5-room, and 3-room flats are much more common in our data, while others like 1-room flats are less frequent. This kind of imbalance is normal in real-life data. There are usually advanced methods to handle data imbalance. We'll try to keep our method simple for this project. Moving on to block. It is the block number of the building. It doesn't really affect resale price unless we analyze advanced features like the block's proximity to amenities and so on. We'll just ignore it for now. Next is street name. Similar to block, this likely will not affect the price significantly, so we'll ignore this too. Moving on to story range. Data present ranges of building stories. They are in string format. We will need to encode them. Story range has 17 unique values. Note that the order in this feature is actually meaningful. Higher stories could have an impact on price. Looking at the distribution, we notice the uneven distribution as before. Let's move on. Okay, floor area in square meters. It's a continuous number representing the size of the apartment. This definitely is useful for predicting resale price, so we'll keep it as such. Take a look at the histogram for this column. The distribution is right skewed, with most properties having a floor area between 50 and 150 square meters. There are some with larger floor areas, but the numbers are clearly very low. There are outliers, and that's not very good for a dataset. This skewness could influence the resale price, as larger properties might actually be more expensive. For flat model, let's check the unique values. Okay, if we get the value count start, we'll see that, okay, model A seems to be the most common one. Some of these types are very uncommon. Moving on to least common state. Okay, least common state is just a year, which makes sense as an ordinal feature, so we'll keep it as is. Let's look at the histogram. It has multiple peaks with a significant number of samples in the 1980s, 1990s, and sometime after 2015. This shows there were periods when many properties were built or maybe the lease got started. Next is remaining lease. Remaining lease is in years and months. The lease period remaining as of sale date, but we don't need this. I'll show you why. If you look at the first row of the dataset, we can actually calculate the remaining lease from the lease commence date and the sale date, which is in the month column. You can tell that the lease was already around 38 years old. Since the total lease that we know is 99 years in HDB, we know now that the remaining lease is around 61 years. So we'll drop this feature to avoid redundancy and to simplify the dataset. Finally, we have resale price. That is our target. If we look at the min and max for this column, the target is ranging from $140,000 to around $1.58 million. This is the label we are trying to predict. What does it look like visually? It is a heavily right skewed graph with most properties falling around 500,000 and a few, very few, exceeding 1 million. We might need to consider this when modeling. Exploratory data analysis, analyzing categorical features and their impact on our data. Let's declare a variable called categorical features, that is town, flat type, and flat model. As we discussed, we will need to encode these features, but we want to take a good look at what we have before we even move further. Let's see what we are working with. df, take a look. Right. First, we'll create box plots for the three features to take a look at outliers that are values that are much higher or lower than the rest of the data. We'll create a grid of subplots. We have three features, so we'll plot them in one row and three columns. Okay, flatten. This function will convert the grid into one-dimensional array that's easier to loop through. You'll see why. We'll enumerate through the list with I for index and feature for each feature name. Okay. Let's give it a title, Outliers in a certain feature. And let's rotate the x-axis parameters by 90 degrees. It looks clearer in the final image. Finally, let's use tight layout function. This automatically adjusts the spacing between the plots so they don't overlap and they'll fit neatly within the figure. Okay, what do we have here? Certain towns like Bukit Timah and central area have significantly higher resale prices. The low box and the longer top whiskers show several properties above 1 million in these areas. Similar plots are found for Kallang, Queenstown areas. And if you look here, areas like Bishan and Toa Payoh show fairly lower median or less spread, but they have plenty of outliers. Other towns have much lower prices and also show many outliers. When it comes to flat types, there's a clear upward trend in resale prices with increasing room sizes. Multi-generation flats have fewer data points. They are less common, but actually more expensive. Flat models. Okay, various flat models show different price ranges. For instance, certain models like these tend to be more expensive. Two-room flats have notably lower prices, indicating they are generally more affordable. Standard flat models seem more common, with wider spread, high variability above the mid 50% of data, and they show very few outliers. The resale price generally increases for larger flat types and more premium flat models. These plots help show that there's more variation in certain categories like 5-room flats or premium maisonettes, which have a wide range of prices. Next, let's visualize the mean resale price using Seaborn's point plots. We'll use a very similar code. Okay, towns like Bukit Timah and central area, which we have seen before, show higher mean resale prices. Yishun, Bedok, and Sengkang have lower mean resale prices. They are suburban locations. The variation within each town is shown by the error bars. Resale prices can vary widely even within the same town, likely due to different flat types, sizes, and proximity to amenities. Okay, flat type. There's a clear trend similar to box plots where resale prices increase as the flat size grows. The error bars are similar for 2-room and 3-room flats. There's less price variability compared to larger flats like 5-room or executive. Flat model. Some models have higher mean prices compared to others. 2-room flats have lower mean resale prices, making them the most affordable options. There's significant variation in prices for certain flat models. Finally, in categorical feature analysis, we can visualize resale price distribution using strip plots. Paste the same code and change the name of the plot here. Okay, the resale prices across different towns vary significantly, but towns like Bukit Timah, Central Area, and Marine Parade stand out with higher resale prices. Suburban towns like Woodlands, Sembawang, and Yishun have lower resale prices. As expected, two-room flats have the lowest resale prices, while larger flats like 5-room and executive flats are much higher in price. Flat models like Maisonette and Premium Apartment Loft have the highest resale prices. Standard and simplified models have lower prices. We'll look at numerical features next. We could use describe. We can get an overview of basic stats like mean, standard deviation, minimum, maximum, and percentiles for numerical features. What do we have here? The statistical summary for 3 columns. Floor area, square meters, lease common state, and resale price. It helps us understand the distribution of these features. Let's break this down. Floor area square meters. The mean is around 97 square meters. That's the average floor area. Standard deviation around 24 shows moderate variability in floor area. There are some much higher and some much smaller flats. Look at lease common state. We can see mean and standard deviation here. Half of the leases commenced before 1996 and 25% commenced after 2011. The leases are quite spread out. Last is resale price. We are looking at scientific notation for resale prices. Mean is the average resale price, which is around $500,000, and standard deviation is around 174,175 actually, showing significant variability in resale prices. 50% median, if you look at that, that's 470,000. That means half of the flats were sold for less than 470,000. So we have a large standard deviation and a wide range of resale prices. This means that some flats are considerably more expensive. But wait, these 3 are not our only numerical features, right? Let's take a look at info. So we have a lot of data, but none of these showed up in describe. So in order for these to make sense, we need to pre-process the data first. So let's take a detour and start data pre-processing now. Pre-processing is an important step in preparing data for modeling. We'll be doing a few things here, like extracting new features, dropping unnecessary features, and encoding categorical variables. What do we do first? Extracting new features. As we saw earlier, the month column contains both year and month in a single string, but we need to separate them for easier analysis. I'll split the month column into 2 new columns. Year of sale, month of sale. Okay, we can drop the month column now. Drop. Okay, in place. Okay, take a look at the data frame again. We now have separate columns to capture year and month of sale. This will help us explore trends later on. Next is dropping unnecessary features. We'll drop features that don't provide any value to the model, like as we saw before, and remaining lease columns. We saw that these columns don't really impact resale prices in any meaningful way. So let's do this. In place, true. This leaves us with a cleaner data set that's more focused on the features that are likely to affect resale prices. Next step is encoding. Why do we need encoding? Many machine learning algorithms, especially regression-based ones like the one we'll use, work with numeric data. Categorical features are in text form, like our town, flat type, story range, or flat model. They cannot be used directly in regression models. Encoding converts these categories into numbers that our model can process. There are many types of encoding, but we'll focus only on 2, label encoding and one hot encoding. Okay, in label encoding, each unique category is assigned a numeric value. This is useful for ordinal features when the categories have a meaningful order or some sort of ranking. Take story range, for example, which represents the flow levels. Like we have 1 to 3, 4 to 6, and so on. There is a natural order. So these will get converted to 0, 1, 2, 3, etc. In one hot encoding, we create new binary column for each unique category in the feature. It's used when the categories do not have any inherent order or ranking. Consider the town feature. We have 26 towns and each town is unique with no sense of ranking. A new column will be generated for each town, marking it as true if the town matches or false if it is some other town. Okay, back to our code. We'll apply label encoding for story range to assign numerical values to each category. We'll have to import label encoder from scikit-learn's pre-processing module. Okay, let's call it encoder. Fit and transform the encoder at the same time. Yeah, we are actually assigning it to a column with same value, so it will just get overwritten. Right, we can now see that our story range column has been encoded and we see numbers here. If we want to refer back to the original categories, the text-based categories at any point, we can use the classes attribute, or we can even look at the corresponding codes that we have assigned by transforming them like this. Next is one hot encoding. For town, flat type and flat model, we'll apply one hot encoding since the order of numbers are not meaningful. This increases the number of columns greatly because, as we saw before, these features have many unique values, but it's a necessary step to handle non-ordinal categories properly. This is how we do this. We'll use pandas getDummies function, pd.getDummies. We'll use the columns like we defined before. Before doing this, note that the values in these columns have spaces or uppercase letters in them. These values are going to show up as column names after one hot encoding. So it's better to handle these first by replacing spaces with underscores and converting everything to lowercase. It just looks neater. We'll take the string, convert it to lowercase first, and then we'll replace spaces with underscores like this. And then we'll repeat this for flat model and flat type. Now we should be able to generate cleaner looking columns. Let's repeat the earlier code. We'll also cast it as int type so that the resulting columns will have zeros and ones instead of Boolean values. Okay, now we have a cleaner looking data frame. Check out the shape of the encoded data frame. Okay, 60 columns now. Let's also confirm the data types and column names using info. This is where we should take another backup of our data frame. We want it after pre-processing. Let's call it df1. What shall we do with it? Let's get the summary statistics. Use describe like we did before. Let's see what we have now. Okay, here's the summary for 60 columns. They help us understand the distribution of these features. Let's look at a few. Story range is a categorical feature and it was encoded to numbers. Remember the encoded classes we've seen before? These numbers are based on the codes that we had from label encoding. The next three columns are continuous numbers and we've already seen these before. Sale year and month look pretty well spread out. The remaining categorical features like town, flat model were converted to binary format previously. For these columns, minimum is 0 and maximum is 1. Here the mean tells us the proportion of records that belong to each category. Take for example, town Angmokyo. It has a mean of 0.041, approximately 4.1% of our samples are from this town. We want to observe the correlation between various features and plot them as heat map for visualization. Let's print out the correlation metric. We're looking at a grid of 60 rows and columns, and it's cluttered with so many low impact binary columns created during pre-processing. We don't really need to look at them in the heat map. So instead of plotting a full heat map with all 60 features, we'll focus on key numeric features alone. Let's declare an array of numerical columns here. There are only 6, so it's easier for us to just copy and paste them like this. While we are here, let's also define binary features. We can extract them from the columns attribute by removing the numerical columns like this. Now let's calculate correlations again and name it core_num. This is neater with fewer columns. Let's visualize this using heat map from Seaborn library. Okay, that's looking beautiful. We can easily identify the features with high correlation to each other. Okay, +1 here indicates that there's perfect positive correlation, and -1 means perfect negative correlation. And everything in between can be positive or negative, but just not as strong as this. Here's a breakdown of the heat map. Okay, resale price. It's strongly correlated with floor area, that's 0.6 here, meaning larger apartments are priced higher. Positively correlated with story range as well, there is a 0.35, and also with lease commencement date 0.37, suggesting that newer, higher floor apartments tend to sell for more. Slightly weaker correlation with sale year 0.33, hinting that resale prices have increased slightly over time. Makes sense. Floor area is almost independent of the story. That's what these negative correlations mean. Interestingly, there's some correlation with sale year. Houses have become smaller with time. Next is story range. It correlates positively with lease commencement date, indicating that higher floors tend to be found more in newer apartments and in understandably taller buildings. Newer flats tend to have higher resale prices and are basically taller with higher floors. Correlation matrix can help interpret the factors that contribute to higher resale prices. As we see, floor area, story range, and lease commencement date play very important roles. We can view outliers for numerical features using box plots. Lovely. Significant outliers are present in resale price, floor area, and story range. They represent high-end properties with higher prices, larger floor areas, and higher stories, which might skew the analysis. These may need special handling like scaling or potential removal of outliers if they unduly influence the model. Especially this particular single value seems out of place. The sale year, lease commence date, and sale month do not show outliers, more evenly distributed. We can analyze this further using pair plots to compare two features at the same time, like this. The diagonal plots show the distribution of the particular feature. Let's analyze the first row or column, which shows the relationship of resale price with the other features. Well, floor area is showing a visible linear relationship with the target. Story range is also showing some linear relationship, although not as obvious, meaning the price seems to be a wide range for lower floor apartments, while higher story flats are on the higher price range by default. Against lease commence date, the relationship is not exactly linear. It's just that there are fewer high-end flats regardless of the date. Sale month seems steady, but sale year plot shows the upper price range for flats. It seems to be steadily on the rise over the years, while lower-end flats are still available. Moving on to floor area against the other independent features in the second row here, The plots seem to be influenced by the single outlier which we first noticed in the box plot. One observation here is that the largest and smallest of flats seem to be present only in lower floors. They are probably mansions or independent housing instead of apartment buildings. Story range and least common state confirms what we have already observed. Higher stories are only available in newer apartment buildings. Sale year and month plots don't show any further insights. Okay, moving on. Let's take a look at this particular outlier and analyze it. Dot max shows you the maximum value of floor area in our dataset 366. If we find the rows with this value for floor area, we get this single row, which is our unique outlier. Looks like it is a very recent transaction. Many columns are hidden. Let's get a transposed version. Right, lease started in 1972, sold recently in Town Kalang or Whampoa. It's a terrace type, 3-room flat. Okay, it seems like a genuine entry, but it's definitely out of place. We'll need to handle this because linear regression is quite sensitive to outliers. It can impact predictions and cause misleading results. Now that we are done with data preprocessing and EDA, we are ready to start working on the model. Before we proceed, let's talk about linear regression, one of the most commonly used algorithms in machine learning. Linear regression is a method that helps us understand the relationship between a dependent variable, which is the one we want to predict, and independent variables, which are the features we have. There could be one or more features. The assumption here is that the relationship between the target and the features is linear, meaning we can fit a straight line through the data and it helps make predictions. Okay, let's break this down. Here's the formula for linear regression. Here, y is our predicted value, that's the target, the label, and what we are trying to find. Here, in our case, resale price. X is the input feature, like the size of the house if we are predicting house prices, floor area or story code. M is the slope of the line, which tells us how much y changes for every unit increase in x. And B is the intercept, which is the value of y when x is 0. So our algorithm's job is to find the best values for M and B that make the predictions as close as possible to our actual data. To find the best fitting line, this method uses a technique called least squares. What this means is that it will try to minimize the difference between the actual data points and the predicted points on the line. It's done by calculating the sum of the squared differences and finding the line with the smallest number possible. So why linear regression? When we want to predict a number like sales, prices, or any other continuous value using the factors we already know. Linear regression works best when the relationship between the variables is linear. It is also sensitive to outliers, which can mess with the predictions. If we are using more than one independent variable, you need to check that these variables aren't too correlated with each other, which is a problem with multi-collinearity. Let's start by fitting a simple linear regression model to see how the model performs. I'll first separate the features and target variable. Let's call them x and y. X would be features, which are independent variables, and y is the target, resale price. Let's split the data set into training and testing sets. We need to import train test split from model selection. Okay, we can specify the size of the test split and provide a random state. This is for reproducibility. Here you go. Check out the shapes of our newly created splits. Now we are using 80% of the data for training and 20% for testing. This is what we mentioned as 0.2. This helps us see how the model performs on unseen data. Time to create our linear regression model, fit it with training data, and make predictions on the test data. This is all pretty straightforward. Now that we have trained our linear regression model, it's important to evaluate its performance. Let's go over some common metrics. R square, mean absolute error, mean squared error, root mean squared error. These metrics help us understand how well our model is making predictions and how far off our predictions are from the actual values. R square or R2 measures how well our model explains the variability of the target variable. It ranges from 0 to 1, where 1 means the model perfectly predicts the resale price and 0 means it doesn't explain the variance at all. MAE or mean absolute error, it is a straightforward method that tells us on average how many dollars our model is off. Since it's in the same unit as the target variable, it's easy to interpret. Let's see how this transforms to our dataset. First, we'll need to import these metrics from scikit-learn. Let's find R square. In our case, R square is 0.86. It means 86% of the variance in resale prices is explained by our model. Mean absolute error next. It's around 50,000. This means on average our predictions are off by around $50,000. Since this is in the same unit as the target variable, it's a straightforward way to understand how far our model's predictions are off from the actual resale prices. As a result of our extensive EDA, we know that our dataset comes with a lot of outliers. Let's see if removing the outliers can help improve our model. We'll use a method called IQR, interquartile range, to remove outliers. This method looks at the middle 50% of the data and removes extreme values that's outside a certain range. We'll need to remove outliers for multiple columns. Since we pretty much need to repeat the code for this, let's make it a function. Now we can apply this function to remove outliers for resale price, flow area, and story range. These features have extreme values that could negatively affect our model, so we are trying this out. Okay, now we have a cleaned dataset with outliers removed for these three columns. Check the shape. We should have a fewer number of rows now. Alright, we seem to have dropped around 10,000 rows of data. Sounds huge, but given the size of our original dataset, this is okay. After removing outliers, I'm going to split the clean data and train the model again, just like we did earlier. Let's check the metrics to see if there's an improvement. Okay, our R square dropped from 0.86 to 0.85. Removing outliers slightly reduced the proportion of variance explained by our model. MAE has decreased from 49,000 to 47,000, which is good. On average, the model's predictions are now closer to the actual values, showing improved performance in terms of average error. There is a slight drop in R2. Outliers might have been influencing the model's ability, and removing them makes the model a bit more realistic. Okay, we spoke about scaling and normalization before, but I did not do this here in this tutorial because when I tried it, it did not help the accuracy or the error reduction in any way. Feel free to try it on your own. Let us know how it works. With this, we come to the end of our HDB resale price prediction project. Let's quickly recap what we have done and the insights we have gained throughout this project. We started by exploring the dataset, where we analyzed various features such as town, flat type, flow area, and lease comments here to understand the underlying trends in HDB resale prices. Through EDA, we gained valuable insights on how different flat models and sizes influence the overall resale prices. We also discussed the importance of data preprocessing, including handling categorical variables using label encoding and one-hot encoding, extracting new features and removing irrelevant features. We built and evaluated a linear regression model to predict resale prices. We looked at key metrics like R-square, mean absolute error, to measure our model's performance. Additionally, we handled outliers and we saw the impact of these steps on model performance. In conclusion, this project has shown the power of linear regression in predicting real-world outcomes like housing prices. We've seen the importance of data preprocessing, handling outliers, and using the right evaluation metrics to assess the model's performance. While our model already performs well, there's always room for improvement using techniques like feature engineering, hyperparameter tuning, or even experimenting with other machine learning models. If you enjoyed this video, please like and subscribe to our channel. Let us know in the comments if you have any questions or suggestions for future content. Thanks for watching and see you in the next video.